Hello and welcome to another video, this time on Math Specimen 1 question 3. I thought I'd quickly rattle through this after doing question 2. So another one really with, as I described it in the last video, not much really to this. They're just very good at making it sound like a different kind of question, not like an A-level question, but it is really not that bad. Okay, so we've got this. It's just a quadratic with one unknown, one constant which they might vary in it, where p is a constant, yeah, but they're going to change it, they're going to say they're going to restrict its values. Okay, so show that the function x has one stationary value in that range if p is in that range. Well, I mean, the stationary point is just x equals p. You could see that from completing the square in your head. But okay, I'm going to do it using calculus because, stationary value is where f dash of x equals 0. So 2x minus 2p. Okay, this equals 0. So 2x minus 2p equals 0. So x equals p, yeah? So first thing I'm going to note here is, so if 0 is less than x, yeah, so if 0 is less than p is less than 1, because that's what we've been given, if 0 is less than p is less than 1, then it has one stationary value in the range, because x equals p. Yeah? Right, otherwise, there would be no stationary values in that range. I'm just going to say that because, I mean, it's just obvious. It has to occur when x is p. So if p is between 0 and 1, x must be between 0 and 1. Okay, in the remainder of this question, we'll be interested in the smallest value attained by f of x in the range 0 to 1. Now, this is a very common kind of idea because it trips people up on trying to state the range of a quadratic. Yeah, they forget that it's got a minimum value, so you can't just, if you restrict the values on a quadratic, you can't just chuck in the smallest and largest x value to find the range of the function. You've got to check for the turning point. And that's really, I guess, the point that this question is getting at. Okay, so let's do it. In the remainder of this question, yeah, okay, so m is the y coordinate and it will depend on p, m is the smallest value attained for f of x in the range from 0 to 1, yeah? So basically, with our quadratic, which is constantly varying, or from 0 to 1, we're trying to decide on the smallest value. It might be like that. It might occur at 0, and there's only really 3 possibilities, or it might occur at 1, yeah? So it's either at the turning point, or when x is 0, or when x is 1. Really, you see that, because from 0 to 1, the lowest point is going to be there. From 0 to 1 here, the lowest point is going to be there. Depends where the turning point is, whether it's between 0 and 1 or outside of it. If it's between 0 and 1, then m will equal, the value, you just tuck in x equals p, and that gives you the value of m. Okay, so if p is greater than or equal to 1, m equals 4 minus 2p. Okay, so we already know turning point occurs is at x equals p. We already know that, yeah? That's guaranteed. Okay, show that if p is greater than or equal to 1, then m equals 4 minus 2p. So I'm just going to point out, if p is greater than or equal to 1, then, and it's just, it's good to graph things. Please do delete them what I've done here. These are the 3 possibilities. Here, we can see 0 is less than p, which is less than 1, yeah? I'm trying to show that the turning point is between 0 and 1. Here's where the p is less than 0. And here's where p is greater than or equal to 1. Yeah? So as we can see, we've got a decreasing function here. So I can say then the function is decreasing. You could easily prove that with calculus as well. And so m arises when, so x equals 1 for min value. And if x equals 1, let's go back to our original equation, we're going to get 1 minus 2p plus 3, which is 4 minus 2p. And I've literally, if you're wondering how I did that, I literally plugged in x equals 1, because I knew the turning point would occur. If the turning point occurs after this, then the smallest value on that quadratic is just where x is 1. It's just like that. 3 little diagrams makes this so much easier. Okay, what is the value of m if p is less than or equal to 0? So if p is less than or equal to 0, then the function is increasing. Yeah, this is part 2. So we can just say now our function is increasing. So x equals not 1 but 0 this time for min value, and we're just going to plug in 0. What was it again? 0 minus 2 minus 0 plus 3, so m equals 3. Just to show you I've plugged it in. Okay, part 4. What are they asking for now? Obtain a formula for m in terms of p, valid from 0 to p to 1. Okay, so we want a formula for m in terms of p. We're trying to find a turning point here. Well, we know x equals p, and so what we can do is just chuck in, because f of x is, what is it, x squared minus 2px plus 3. Yeah, so x equals p, so f of p is going to be p squared minus 2p squared plus 3. Remember, this is what m equals, so m equals 3 minus p squared. That's it. That's what you've got to do. There's your formula. Okay, using the axes opposite, so there were some axes I sketched out for you. Sketch the graph of m as a function of p in a range of minus 2 less than equal p is less than 2. So this is going to be a piecewise function, 100%, because as you can see, you've got to draw the graph of m again as a function of p. That's like x as a y as a function of x. So m is going to be on your y-axis and p is going to be on your x-axis. Yeah. So m of p is going to be equal to, okay, 3 when minus 2 is less than or equal to p, which is less than or equal to 0. It's going to be equal to 3 minus p squared when 0 is less than p, which is less than or equal to 1 or less than 1. And then 4 minus 2p is going to be the case for when 1 is less than p, which is less than or equal to 2. Or we go from minus 2 to 2, inclusive. Yeah, cool. Okay, it doesn't really matter too much where you put those inequality, strict inequality signs. Just make sure that there's no, there we go. I probably should let p equal 1 here. You get 2 coming out of it either way, so it doesn't matter whether you put it there or there, because it doesn't change the graph or the behaviour. Okay, so now we've just got to sketch this piecewise function of m against p. Well, from minus 2 to 2, what's it going to do? Well, from minus 2 to 0, it's just 3. And this is the m-axis, and this is the p-axis. Then it kind of goes as part of a quadratic, the 3 minus p squared quadratic, which just looks upside down and goes like, it's perfectly symmetrical around here, goes through root 3 and minus root 3. The graph of m equals 3 minus p squared, and that's the p-axis and that's the m-axis. Yeah, it's the same thing. And it does that till it gets to 1. And then it just kind of goes in a straight line down because it uses the 4 minus 2p gradient, so it goes like that. Make sure that's clear that that's flat. That's clear that that's like a little corner of this quadratic. It's just basically this little bit of this quadratic going from there to there. But then it goes in a flat line there like that. Try your best to sketch that in the exam as neatly as possible so they can see a little bit of a curve. Don't think you're allowed to use colour like I'm doing, but I'm just trying to make it clear on the video. Okay, so I hope you enjoyed that. Hope you found it was useful. Best of luck in Step on a Map.